In this video we're going to have a look at first order differential equations, and in particular the integrating factor method. So let's take a look at this example here. It says solve dy by dx log x plus y over x equals sin x. Now in this example what you're supposed to do is spot that this here is a differential made using the product rule. So as a reminder, the product rule is the differential of u times v equals v du by dx plus u dv by dx. And we can spot that this side here is of that form. Plus c. In fact, let's call that c1 because we're going to use another constant in a short while. So now the integral of the right hand side dx, i.e. integrating both sides with respect to x, equals minus cos x plus c2. So that implies that the left hand side, y log x plus c1 equals minus cos x plus c2. Taking all the constants over to one side, y log x equals minus cos x plus c2 minus c1. Well, actually these two constants here, we needn't have put constants on both sides because what we've got here highlighted blue is just a number. So those two constants can combine into one constant. So looking back at this here, we're never in future going to put a constant on the left hand side, simply because we don't need to. So we can just put the constant on the right hand side. So minus cos x plus c, deleting all those constants, only ever put the constant on the right hand side, perfectly acceptable. So it says dy by dx e to the x plus y e to the x equals x sin x. So what we've got to notice again is that the left hand side is a product rule. So it's always a safe bet that y is u, so that when we differentiate that with respect to x, du by dx is dy by dx. So we differentiate y with respect to x, we get dy by dx. Okay, so that makes that one v. And let's check if we differentiate e to the x. We get e to the x. Well, we certainly do. We know that. Therefore, reversing the product rule, the integral of the left-hand side dx equals, well, it's just uv. So y e to the x. The integral of the right-hand side, however, is a little bit more in depth. We're going to have to use integration by parts here. So let u equal x, which means that du by dx equals 1. And we're going to let dv by dx equals sin x, which implies v equals the integral of sin x dx equals minus cos x. Therefore, the integral of the right hand side dx, I'm just looking here, I forgot to write dx before, so let's write dx here as well. That's important. So the integral of the right hand side dx equals uv minus the integral of v du by dx. Okay, equals minus x cos x plus the integral of cos x dx. Double minus makes a plus, which is equal to minus x cos x. The integral of cos x is sin x, then plus c. Therefore, we get the left hand side is y e to the x equals minus x cos x plus sin x plus c. And there, we've done that one. But now we're going to make it slightly more complicated. So take this example here. Solve x squared dy by dx plus 3xy equals sin x over x. So let's see if this is the form of the product rule. So as before, y was a good candidate for being u, because when we differentiate it, we get dy by dx. So this is u, and dy by dx is du by dx. So this means that this must be v. So if we differentiate v, i.e. x squared, we get 2x, not 3x. So the left-hand side in this case isn't of the form of the product rule. So let's get rid of those. But notice, if we times both sides by x, we get x cubed dy by dx plus 3x squared y equals sin x. And now notice that the left hand side is of the form of a product rule, because y, if we let that equal u, if we differentiate to get du by dx, that gives dy by dx. That must mean that this is v. If we differentiate v, we definitely get 3x squared. X cubed differentiated is 3x squared. So now we can integrate both sides. So I'm not going to do that yet, because the thing I want to point out, the real point of this is, how did we know to times by x? Because it really wasn't an obvious thing to multiply by. So we're going to introduce something called the integrating factor method. Which says that when we have a differential equation of the form dy by dx plus p of x times y equals q of x, another function of x. So here p of x and q of x are just functions of x, of p of x dx. So let's try and apply this now to the example that we just had. So this one here. So let's delete all this now. Let's try and find the integrating factor. Well, currently, this differential equation here isn't in this form. It's not the form dy by dx on its own plus a function of x times y equals a function of x. We can see that there's an x squared attached to the dy by dx, whereas really we need nothing attached to dy by dx. So let's then rearrange it into the required form to get the integrating factor. So dividing by x squared, we get dy by dx plus 3 over x times y equals sin x over x cubed. So now we've got it in the desired form. We've got dy by dx on its own there. We've got a function of x times y, and then we've got on the right hand side just another function of x, like that. So now let's find the integrating factor, which is e to the integral of p of x dx. So the integrating factor equals e to the integral of the thing times by y, which is 3 over x dx, equals e to the power of 3 log x equals e to the power of, and let's tidy this up a bit. Let's use the logarithm law, the power rule, and bring that 3 up into the power of x. So e to the log of x cubed, which we know simplifies to just x cubed. So that's our integrating factor. And what our integrating factor does is, if we times both sides of our first order differential equation written in that form, if we times both sides by the integrating factor, we'll end up with a product rule. So let's do it. Let's times both of these sides by x cubed. So we end up with x cubed dy by dx plus 3x squared y equals just sine x, exactly what we got before. So here, this is our u, so this is our du by dx, this is our v, and this is our dv by dx. So therefore, if we integrate both sides, and I'm going to skip a little bit of working here because we're short of space, integrate the left-hand side, bearing in mind we said this was our u, and this was our v. We get x cubed y, and integrate the right hand side, we get minus cos x plus c. And that's the integrating factor method. So let's now put this into practice in an exam question, and once you've done a few of these, they become relatively straightforward. So have a look at our exam questions on this, do 5 or 6 of them, then you'll certainly become a lot more fluent with the method. So let's have a look at this exam question here from 2008. So it says, find the general solution of the differential equation dy by dx plus y over x equals sine 2x, expressing y in terms of x in your answer. So with this one, we need to get it of the form dy by dx, as we saw before, plus p of x y equals q of x. Well, luckily it's already in that form. The dy by dx is on its own. We've got a function of x attached to y, i.e. 1 over x attached to y. And on the right-hand side, sine 2x is just a function of x on its own. Therefore, our integrating factor is going to be e to the integral of p of x, i.e. the integral of 1 over x dx equals e to the natural log of x equals just x. So our integrating factor is x. If we times everything by x, then it should give us a product rule on the left hand side. So let's do that. Let's times everything by x, which means that x dy by dx plus y equals x sine of 2x. And indeed we can see there's a product rule on the left hand side, because if I write a 1 in front of the y, then the y is our u, so when we differentiate to get du by dx, we get dy by dx, so y differentiates to dy by dx, and our v differentiates to 1, so x here differentiates to 1. So we've got our product rule where that's u du by dx, and that's v, and that's dv by dx. So if we integrate it, we just get uv. So the integral of the left hand side dx equals just xy uv. Now the integral of the right hand side is a little bit more difficult. It's an integration by parts. So the integral of the right hand side dx, well, if we let u equal x, which means that du by dx is 1 using the integration by parts. You're given the formula for that in the formula booklet. And we've got dv by dx equals sine of 2x, which implies that v equals minus 1/2 cos of 2x. So our integral equals, I should really put the dx, that's important. So the integral of the right hand side dx equals uv. So minus 1/2 x cos 2x minus the integral of v du by dx. So the integral of minus 1/2 cos of 2x dx equals minus 1/2 x cos of 2x, double minus makes a plus, the integral of 1/2 cos x cos 2x dx, which is equal to minus 1/2 x cos 2x, and the integral of that is 1/4 sine 2x, so plus 1/4 sine 2x. So we've got the integral of the left hand side and the right hand side. Therefore our answer, well, the left hand side is xy and the right hand side is minus 1/2 x cos of 2x plus 1/4 sine of 2x plus c. But notice the question specifically asked for y in terms of x in the answer, so we need to rearrange this to say y equals, well, that's just a case of dividing by x to give y equals minus 1/2 cos of 2x plus 1/4x sine of 2x plus c over x. So there's the answer to part 1 of the question, y in terms of x. Now moving on to part 2, which is there. It says in a particular case, it's given that y is 2/pi when x is 1/4 pi. Find the solution of the differential equation in this case. So basically it's asking us to find the particular solution, i.e. find the value of c here. So that's what we're going to do. So we're going to let y equal 2/pi and x equal 1/4 pi. And that means that 2/pi equals minus 1/2 cos of 2 lots of pi over 4 plus 1/4 lot of pi over 4 sine of 2 lots of pi over 4 plus c over pi over 4. So evaluating that, cos of 2 pi over 4 or cos of pi over 2 is 0 and sine of pi over 2 is 1, so we can cross that term out as well. So that gives us 2/pi equals, so here on this term here, the 4 and the pi over 4, a little bit of cancelling goes on just to give 1/pi. Plus, and c over pi over 4 is 4c over pi. Which means that 2/pi equals 1 plus 4c over pi, which means that 1 plus 4c equals 2, which means that 4c equals 1, which means that c is simply 1/4. Therefore, rewriting the differential equation out, we get y equals minus 1/2 cos 2x plus 1/4x sine 2x plus 1/4x. So that's the answer to part 2. We can see part 3 at the top of the screen there. It says write down a function to which y approximates when x is large and positive. So we're going to let x become large and positive. So let x approach infinity, which means that, well, this function here, 1/4x, approaches 0, So as the denominator becomes larger and larger, 1 over 4x approaches 0. So this in turn implies that y will approach minus 1/2 cos 2x. Because these approach 0, 1 over 4x approaches 0, which means this term will disappear and this term will disappear. Then we just get this function here. So the function to which y approximates is y equals minus 1/2 cos of 2x. And that is the answer to the third part. So what we haven't done here, we haven't proved why the integrating factor method works. We've just proposed it and used it. I'm going to do another video which you can look at and it actually proves why the integrating factor method works. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to alevelmathsrevision.com.